Welcome to This Explainer. Listen, today we are stepping straight into the system terminal for a Silicon Valley-style Cambridge exam hackathon. We are going to dive directly into the mind of a principal examiner and hack the ultimate assessment framework. If you're studying AS and A-level mathematics, specifically Paper 2, you already know that facing down complex, multi-part problems can honestly feel like trying to decipher completely foreign source code. It's intimidating, right? But today, we are going to treat these exam questions exactly like an algorithm. Think of Cambridge Mathematics 9709 as our target mainframe. Now, I want to introduce you to two coders we've got on our team today. First up is Dev Alex. Now, Alex is incredible at raw data inputs, but constantly causes memory leaks on the exam because of poor superficial analysis. And then we have Dev Sam. Sam is an absolute genius at logical loops and understanding the theory, but constantly fails the syntax precision rules that examiners demand. By the time we finish this session, you are going to learn from both of their mistakes, read the examiner's source code, and output the exact syntax they're looking for when it comes to complex numbers. Let's get compiling. Now, what's really interesting about this right here is that this single topic accounts for a massive 15% of your total marks on Paper 2. Think about that for a second, 15%. Understanding the polar form of complex numbers isn't just some minor subroutine you can skip over in your revision. It is an absolute, critical system requirement for a high grade. It's the core functionality. If your methodology here is flawed, like our friend Dev Alex, who just tries to plug and play without understanding the architecture, you're going to experience massive memory leaks in your final score. You just can't afford to drop these marks.
So, to secure those marks, our explainer today will navigate through three main phases. 1. Core theoretical architecture. 2. Technical methodology. And 3. Evaluation and examiner insights.
Okay, let's dive into Section 1, Core Theoretical Architecture. This is where we build our blueprint.
Right, so this central equivalence is the absolute bedrock of the topic. Burning this into your memory is your very first step to unlocking true analytical depth. The polar form, r times the sum of costheta and I sine theta, is mathematically identical to the exponential form, r times e to the power of I theta. Now, Dev Alex looks at this and just sees a formula to memorize. But it's not just a formula, it is a translation key. It's an API that lets you communicate between two completely different formats. Toggling into that exponential form makes multiplying, dividing, and finding roots of complex numbers incredibly efficient compared to standard algebra. Knowing how to instantly switch between these two forms allows you to manipulate complex data inputs effortlessly. You literally become a more efficient processor of math. Here is where we really start clearing the examiner firewall. Principal examiner reports explicitly state that candidates who connect this theory to other syllabus areas achieve significantly higher scores than those who don't. The examiners aren't just looking for isolated lines of code or basic calculations, they want to see full-stack integration. Can you link the geometry of the Argand diagram to the algebra of polynomials? Can you connect it to the calculus of trigonometric functions? Connecting these dots is exactly what upgrades your grade from standard to premium. Dev Sam gets this, but often fails to articulate it clearly. You need to see the whole system matrix, not just the individual data points.
And this brilliantly illustrates the difference in the entire assessment framework. Cambridge completely prioritizes deep, logical reasoning over simply memorizing a wide array of disconnected facts. It's the classic battle of superficial breadth versus analytical depth. Superficial breadth is Dev Alex. It's like having a giant glossary of coding terms memorized, but having absolutely no idea how to write a functional script. Analytical depth, on the other hand, means you actually understand the causal relationships. You can track the logic from the very first line of your proof, step by step, all the way to the final compiled output. That is what we are aiming for here.
Let's move straight into Section 2, Technical Methodology. This is the method mark strategy, and it is crucial. We are debugging the command matrix right now. Examiners want to see you execute this precise three-step problem-solving algorithm. Step 1, deconstruct the given information. Step 2, solve systematically. Step 3, evaluate and check for reasonableness. Think of this as your primary logical loop. First, you deconstruct the text and extract your variables. What are your inputs? Second, you apply your systematic operations. This is where your equivalence formulas come into play. You write the pseudocode for your proof. Third, you evaluate the output. Ask yourself, does an angle of 3 pi over 2 actually make sense for a principal argument? Well, probably not, right? Because the system constraint requires the principal argument to be between negative pi and pi. So you need to adjust it to negative pi over 2. You have to check your logic and debug your own work before you move on to the next line. Hold up, before we push this final patch to secure those maximum marks, we need to optimize your system feed. Subscribe to Ace the Exams at Ace the Exams right now and turn on all notifications for weekly system updates. Okay, resuming the compile. To clear the examiner's rigorous standards, your presentation of information must strictly follow these professional conventions without exception. Proper headings, correct terminology, appropriate formats, clear annotation. This is where Dev Sam completely crashes. Sam has the logic but ignores the syntax. Just like a single missing semicolon can crash an entire computer program, using the wrong terminology or dropping a crucial notation in your polar form can result in 0 method marks. 0. So I want you to deploy a syntax structure like PEEL. Even in math, point out your theorem, provide your numerical evidence, evaluate the constraints, and link your final output back to the exact prompt. You have to format your reasoning clearly, annotate your diagrams on the complex plane, and prove to the examiner that you speak their exact mathematical language fluently.
And that brings us to Section 3, Evaluation and Examiner Insights. Time to avoid the traps. Welcome to the interactive beta testing arena. So the crucial point here is this major siren directly from the examiners. The classic mistake is providing generic answers not specific to the question context. I want you to imagine a 60-second visual countdown clock ticking away in your mind right now. Run a trend extraction on this. What does it mean? It means you should never, ever drop a rehearsed generic answer that completely ignores the unique scenario provided in the prompt. If the question asks about a specific transformation in the complex plane, do not just vomit out a standard textbook definition of modulus and argument. You must adapt your base knowledge to the exact, specific parameters of the question that is right in front of you. Generic code simply will not compile here. All right, let's run Test 2, the code review. These are the top 3 memory leaks, the fatal errors that actively drain candidates' scores and turn solid theoretical knowledge into completely wasted method marks. Number 1, using the wrong approach for the context. For instance, struggling with Cartesian form when polar form is vastly more efficient for multiplication or division. Number 2, forgetting to check format and presentation. Like we talked about, leaving your argument outside the required range of -pi to pi. That's a classic syntax error. And number 3, providing non-specific generic answers. Avoid these 3 memory leaks, and I promise you, you instantly optimize your exam performance. We are finally at the code deployment phase. Top-scoring candidates always deploy context-specific outputs by questioning their own assumptions and evaluating the exact evidence quality in front of them. Look at the difference. A generic output is writing R represents the distance. Okay, sure, but a context-specific output is writing R represents the radius of the locus circle in the complex plane based on equation X. Boom. The latter proves you aren't just reciting a memorized line of code. It proves you are actively analyzing the architecture of the specific problem they gave you. That is how you secure the maximum possible score. So as we finalize our cheat sheet architecture, before you tackle your very next past paper, I want you to look at this question and evaluate your own process. Are you simply calculating an answer, or are you strategically evaluating the context to secure every single method mark? Don't just be a basic calculator, be a system architect. Plan your responses, follow the strict syntax conventions, and adapt your knowledge to the specific constraints of the prompt. The examiner has handed you their source code. The only question left is, are you ready to compile a flawless score? Thank you so much for joining me for this explainer. Keep optimizing your systems, and hey, make sure to subscribe to Ace the Exams. At Ace the Exams, click that bell, and leave a comment down below with your specific subject and level so we can keep these patches coming.